Hey everyone, to close out this semester, I want to give you a little bit of an introduction to Bayesian statistics. I'm a Bayesian statistician, so this is kind of my bread and butter. The other class I've been teaching this semester is an introductory class on Bayesian statistics, so this is sort of the starting point for that class. This is going to be a set of 3 lectures. The first of these lectures is an introduction to the ideas behind Bayesian statistics. So let's get started with that. So there are 2 main types of statistical inference. And those 2 types are frequentist inference and Bayesian inference. Frequentist inference and Bayesian inference have been around for, well, pretty much as long as statistics. Bayesian inference has to do with an application of Bayes' theorem, which we learned earlier in the class, to doing inferential work, to doing things like point estimation, confidence intervals, or interval estimation, testing. Those are inferential procedures, and so there are 2 different ways of approaching those, or 2 common ways of approaching those. So like I was saying, frequentist inference methods are the ones that we learned in the previous chapter, and now I'm going to start talking a little bit about Bayesian inference methods so you have some idea of how these work. Let's talk first about how to distinguish between these 2. What are the 2 big differences between Bayesian inference and frequentist inference? So one of the main differences is what we consider fixed and what we consider random in frequentist and Bayesian inference. So I'm writing theta is fixed, x is random for frequentist inference, and for Bayesian, x is fixed, theta is random. What do I mean by this? Remember that theta is what we use to denote sort of a generic parameter for a statistical model. And x is what we use to denote generic data for a statistical model. And so the frequentist perspective says that the data are random and the parameters are fixed. And so, for example, let's say I want to look at heights of a bunch of students. There's going to be an average height for that collection of students, and that average height I can think of as a parameter, like theta. And then the individual students, well, I'm going to go sample a bunch of individual students, and those students are going to be random draws from the distribution, from the population of students, and so their heights will be random. So the frequentist idea is that there is some overall average height that exists out there in my population. And then I'm going to take draws from the population randomly. And the people I see randomly, those are random draws from a population of heights with mean theta. How is the Bayesian thinking about this? So it seems pretty reasonable to think of random draws from a population as fixed parameters. The Bayesian is flipping this around and saying that x is fixed and theta is random. What does that mean? Well, in practice, when we collect data, we collect data. The data is known to us. X is fixed. So if I have a population of people and I sample a bunch of them and I see their heights, I have seen their heights. Their heights are known. That is no longer a random thing for me. I know those heights. The thing that I don't know, that I want to usually do inference on, is that average height, that parameter of the distribution. And so Frequentists think about the distribution as being a fixed thing, the parameters of the distribution as being fixed values, and data as random draws from that distribution. Bayesians flip that around and say those draws from the distribution, those draws from the population, those are the things we know. We've gotten to see those. We've collected the data. And so the thing we don't know is we don't know the value of the parameter. We don't know the particular properties of the distribution governing that data. What does this get for us? Well, in Bayesian inference, this gets us our inferences are going to make statements about the parameter. Oh, I need to erase that. So in Bayesian inference, our inferences are going to make statements about the parameter theta and properties of the distribution of theta. In frequentist inference, instead, since the data are the thing that we consider fixed, our inferences are going to talk about how appropriate the data seem based on assumptions about the parameter, since the parameter is considered to be a fixed value, just an unknown fixed value. Let's look at that in the context of hypothesis tests and confidence intervals. So we've learned about hypothesis tests and confidence intervals as a frequentist. In hypothesis testing, we have this value called the p-value. And the p-value is p-value is the probability of seeing data as weird as what we saw or weirder, conditional on the null hypothesis being true. And remember, our null hypothesis is going to look something like h0 theta equals theta naught. h1, our alternative hypothesis. Don't want equals there. Our alternative hypothesis states that, so colon, theta not equal to theta naught. So that's a common hypothesis testing example. I have some value I think might hold true for theta. That's my null hypothesis, and I want to test the alternative hypothesis that that value doesn't hold true. So what does a p-value mean for me in hypothesis testing? A p-value means did the data that I see, are those data consistent with the hypothesis that the true value of theta for the population these data are coming from, that value of theta, it may in fact be theta 0. So I can write P is equal to probability of data given H0. So that's what I get when I do a frequentist hypothesis test. I get this p-value. The p-value is a conditional probability. It's the probability of seeing data as weird as we saw or weirder, given that the null hypothesis is true. And this leads us into that discussion of type 1 and type 2 errors. What's the probability that I reject the null hypothesis when it is in fact true? What's the probability that I accept the null hypothesis when it is in fact false? The first of those is type 1 error, rejecting the null hypothesis when it's true. Second is type 2 error. So I'm conditioning on whether or not the hypothesis is true, and I'm saying what's the probability of seeing my data? This is what we expect to see as frequentists. The thing that's random are the data. The thing that's not random is theta, is our parameter. And so we make an assumption about our parameter theta, and then we say, do the data that we've seen accord with that assumption or not? So that's how we run this problem from a frequentist perspective. What does this look like from a Bayesian perspective? I'll move a bit more down. Okay, so if my idea with hypothesis testing is to choose between two hypotheses, well, how is the Bayesian going to treat this problem of choosing between two hypotheses? So Bayesian's just going to ask, is the probability of the null hypothesis greater than the probability of the alternative hypothesis? And as a Bayesian, I can construct an inferential procedure that will let me do this. How do I feel about this? This is a little bit different from what I'm doing as a frequentist. So as a frequentist, like I said, we're looking at what's the probability of seeing some data conditional on some value of the hypothesis. As a Bayesian, I'm just asking which of these hypotheses is more likely. Well, that seems a little more intuitive, doesn't it? I have two competing hypotheses, and I want to ask which of them is more likely. Is it more likely that hypothesis 0 is true or that hypothesis 1 is true? Problem is, as a frequentist, that's not a question I can ask because theta is fixed. There is a true value for theta that lives out there in the universe somewhere, and I just don't know what it is. And so from the perspective of a frequentist, either hypothesis 0 is true or hypothesis 1 is true in this case. Either the null hypothesis or the alternative hypothesis is true. One of these has to be true. And so there's no way to consider what happens. There's no way to consider a probability of one being true or not. I think I did an example like this back when we were still meeting in class. And so let me give that to you again now. Say I flip a coin. If, well, the coin is in the air, I ask, what is the probability of getting heads? A frequentist and a Bayesian will generally agree. And assuming that this is a fair coin, they'll agree on P of heads is equal to 0.5. So I let the coin fall, and I put my hand over it, and then I ask the question. Generally speaking, a Bayesian and a frequentist will disagree. To the Bayesian, probability is still 0.5. I haven't gotten to see the coin. The probability the coin landed heads is 0.5. To the frequentist, probability of heads is equal to 0, or probability of heads is equal to 1. But we don't know which it is because we haven't gotten to see the coin. It's been decided, though. The coin has been flipped. There is no probability left. Bayesians assume that anything I get to see is something that is fixed. Anything I don't get to see is something that's random. Frequentists assume that the underlying properties are fixed, and that things that I observe are random. And so how this shakes out for us is the frequentists, the event has happened, and so there is no longer a probability. Either the coin is heads or the coin is tails. And so either the probability that the coin is heads is 1 if it's been flipped and it's gotten heads, or it's 0 if it's been flipped and it's gotten tails. There is no longer probability, a meaningful probability associated with this. But for the Bayesian, because the Bayesian doesn't know, the probability is still 0.5. That's still a meaningful statement. And so this is the long-run frequency interpretation of probability, which is where we get the name frequentist. That frequentists base their ideas on probability around this long-run frequency interpretation. The long-run frequency interpretation says an event has happened, and whether or not I know what it is, it's happened, and so there is a frequency for the event. The Bayesian accepts the idea of subjective probability. That probability is a thing that lives in someone's head, and so even though the event has happened in the world, because I haven't gotten to see it, for me, the probability of heads is 0.5. For someone who's gotten to see it, then their probability might not be 0.5, but people can have different probabilities for an event. For a frequentist, there is a probability for the event. There is a state of the universe, and that determines it. Okay, let's go back to hypothesis testing. So, like I was saying, for the frequentist, there is a true value of theta. Either theta equals theta 0 or theta doesn't equal theta 0. And so all we can talk about here is what's the probability of seeing data like we saw, assuming that theta 0 is true. All I can do is I can either assume theta 0 is true or I can assume it's not true and move forward from there. What the Bayesian does is the Bayesian assumes neither, and the Bayesian gets to talk about what's the probability of hypothesis 0 being true versus hypothesis 1 being true, the null hypothesis versus the alternative hypothesis. So if I'm interested in which hypothesis to choose, this is a pretty natural way to look at it. I'm just asking which hypothesis do I think is more likely, and I don't subjectively believe either one is true because I don't have data that proves to me that either one is true. So how does a Bayesian consider this problem? Let's scroll down a little bit more. I'm going to run out of room here, but that's okay. I'm about done with this lecture. So Bayesian hypothesis testing is going to consider two values. The probability of the null hypothesis given the data x versus the probability of the alternative hypothesis given the data x. And if the probability of the null hypothesis given the data x is larger than the probability of the alternative hypothesis given the data x, then we prefer the null hypothesis. So what we'll often do is we'll combine these guys up into a ratio. And so what's going to happen with this ratio? Well, if this ratio is 1, if this ratio is greater than 1, that means that my numerator is greater than my denominator. Probability of seeing the null hypothesis, probability that the null hypothesis is true is greater than the probability the alternative hypothesis is true. Alternatively, if I have a number less than 1 for this fraction, then that means that my denominator is bigger than my numerator, and the probability of the alternative hypothesis being true is greater than the probability of the null hypothesis being true. So, point of all this is to give you a little bit of a flavor of the difference between thinking of inference as a frequentist and thinking of inference as a Bayesian. In the next lecture, I'll look at how we actually get something like the probability that the null hypothesis is true given x, or we'll actually start a little bit more basically, but the next lecture is going to be getting into the idea of this type of distribution, which is something I call a posterior distribution, and how I find a posterior distribution given a prior distribution, my prior beliefs about the null hypothesis, and a likelihood. We've talked about likelihoods now. What the data x says about the likelihood of it says about how likely it is that I have a particular parameter value. So that's what we'll get into next time.